Hi class, today we're dealing with section 1.3, average rates of change. The last two sections we covered limits, and now we're doing average rates of change. We're getting a little bit closer to doing calculus. The objectives of this section are to compute an average rate of change and to find a simplified difference quotient. Let's get started. First, let's go over the concept of what an average rate of change is and how does it differ from an instantaneous rate of change. Well, to do this example, let's imagine that you have a friend who lives 60 miles away from you. And so you want to drive to their house. And so you drive there and it takes you about an hour to get to their house. You can say that the distance that you covered is the amount that you changed in the amount of time that you got there. You would say 60 miles per hour. And so that would be what we call the average rate of change. Now, the instantaneous rate of change would be at any given moment how fast you're going. What we would say is that even though we drove approximately 60 miles per hour to get to our friend's house, we weren't driving 60 miles per hour the entire time. Maybe you were at a stoplight, or maybe you were on the freeway, or maybe you were just pulling out of your driveway. But each of those times that I described, you might be stopped, you might be going 75 miles an hour, or maybe you're only going 25 miles per hour on the streets. And so at any given point, you would have a specific speed, but we talk about the average speed that you had for the entire trip as 60 miles per hour. And so right now we're talking about the change over a long period of time versus an instantaneous rate of change. For question 1, it asks us to state the average rate of change for each situation. And it also tells us to include our units. We always need to include our units. And to be able to find the average rate of change, we want to find the change in one variable divided by the change in another variable. So we have the change here listed as 250 miles and 10 gallons of gas. And so we're just going to say 250 miles divided by 10 gallons. And we can simplify that. That would be 25 miles per gallon. Now I could write it as miles divided by gallons, but miles per gallon actually is a unit that we know, so I'm going to write it that way, mpg. The next question says, it rained 4 inches over a period of 12 hours. So the 4 inches is how much it changed. The 12 hours is the amount of time it changed in. And so we're going to say 4 inches over 12 hours. And so that would be 4 over 12 reduces to 1/3. It would be 1/3 inch per hour. And we always want to state it as if the coefficient is 1. So notice that we did 250 divided by 10. This is 25 miles per 1 gallon. This is 1/3 inch per 1 hour, if we were to put that number in there. This next question for us, part C, asks us to find the rate of change, but it doesn't give us how much changed. We have to figure that out. So from 2 p.m. to 5 p.m. would have been 3 hours. And then we also have the temperature changed, and it went from 82 degrees to 76 degrees. It dropped 6 degrees. So then we would say negative 6 degrees over 3 hours, which would be negative 2 degrees per hour. For this last question, you might be wondering, why did I divide by hours? Typically, we do a change over a set amount of time. And notice that we did the change in inches per hour. You also know, in the example I gave the last screen, we said miles per hour. Typically, the time will always be the denominator, and then any other thing that changes would be in the numerator. So we're going to put the degrees on top and the hours on bottom. Also, keep in mind that I said it dropped from 82 degrees to 76, so we needed to include that negative as well. These are all important details to consider whenever you're looking at a word problem. Now we're going to go over an algebraic definition of the average rate of change. If you recall what I said at the beginning of the other example, I said the average rate of change is when we take the change in one variable and divide by the change in another variable. You might recognize this as slope, y2 minus y1 divided by x2 minus x1. Let's see what it looks like on the graph. The y2 minus the y1 is the change in the y variable, while the x2 minus x1 is the change in the x variable. Notice that when we have this function, we also call y2 f of x2, and y1 would be f of x1, meaning that we're taking the points x1 and x2 and plugging them into f function. So you might get an alternative definition over here. Either way, when we find that, we're basically finding the slope of the line that connects the two dots. So the slope of this line is the same thing as finding the average rate of change because it's exactly the same as the slope formula. We have a special name for this line. The line that connects 2 points on a function is called the secant line. And the slope of the secant line gives us the average rate of change. For a function that has curves, the average rate of change will be different depending on which x values are picked. So let's see what the average rate of change is for the values that are picked here. Let's call our first value x1 and our second value x2. And then when we plug that in, we'll get f of 4 minus f of 2 over 4 minus 2. In order to solve this, we need to know what f of 4 is. So that would be 4 squared, or 16. We need f of 2, and 2 squared would be 4. And then 4 minus 2. 16 minus 4 is 12, and 4 minus 2 is 2. And so we end up with 6. The average rate of change from 2 to 4 would be 6. Now let's find the average rate of change from 2 to 3. We set up our function to be f of 3 minus f of 2, and you want to make sure that your denominator is in the same order, 3 minus 2. F of 3 would be 3 squared, f of 2 is 2 squared, and 3 minus 2. So we get 9 minus 4 is 5, 3 minus 2 is 1, so the average rate of change is 5. Okay, now we're going to get f of 4 minus f of 3 over 4 minus 3. Once again, as long as you make sure that these x values match up, then we're okay. F of 4 would be 16 minus f of 3, which is 9, over 4 minus 3. You get 7 over 1, which is just 7. Now we have on the screen something that looks like a new definition, but it's actually the same definition that we had before. Notice that I still have the points x2 and x1, and so the change in my x variables would be x2 minus x1. But now we have new names for them. We call the difference between x2 and x1 h, meaning if I go start at x1 and I add h, I'll be over here at x plus h. Now I don't have to worry about calling it x2 and x1. This point here is just x. This point here is just x plus h. And then when you plug them into the function, you're going to get the difference in their y values. Notice that it's now f of x and f of x plus h to match the names of the values that we picked over here. So to write that slope formula, we would write the difference in their y values, f of x plus h, minus f of x. And then we're going to subtract their x values, x plus h minus x. But we can simplify this. X plus h minus x just becomes h. And so we have the average rate of change, and it's the same as the difference quotient that we've been practicing. Let's practice again. Just to help us make a little bit of sense of how the difference quotient relates to the average rate of change, doing a question like this, where we're talking about x is equal to 4 and h is equal to 3, would be similar to saying x1 is 4 and x2 is 7. Notice that the difference between 4 and 7 would be 3. That's why h is 3. But instead of plugging in values like that, we're going to plug it into the average rate of change formula using the difference quotient. So I would say f of 4 plus 3 minus f of 4 all divided by 3. That's f of 7 minus f of 4 divided by 3. F of 7 would be 7 squared. F of 4 would be 4 squared. And so that average rate of change would be 11. Let's do it again. Notice over here I have f of 4 plus 1 minus f of 4 because we're plugging into this difference quotient. And I end up with f of 5 minus f of 4. And I end up with 9. Doing the same average rate of change with the last numbers, notice that my h is getting smaller and smaller, and I kept my x the whole way throughout. F of 4.1 is 16.81. F of 4 is 16. And so that would give me 0.81 divided by 0.1. And so then the average rate of change would be 8.1. For video example 3, we actually found the difference quotient given specific x and h values. We found it several times. What I want to do now is, with the exact same function, find the difference quotient just for that function first, and then we can plug in our values later. In order to do this, we do need to solve for f of x plus h. So I'm going to do that on the side. F of x plus h is the same thing as saying x plus h squared, which is x squared plus 2hx plus h squared. So I'm going to take that and plug it into our difference quotient. And so I will get x squared plus 2hx plus h squared as my f of x plus h minus x squared for my f of x, all divided by h. When I simplify this, I end up with 2hx plus h squared over h. Let's simplify that a little bit more. We'll factor out an h. I'll be left with 2x plus h. And we'll simplify that a little bit more. And then we'll be left with 2x plus h. Therefore, whenever I get a value of x and h, instead of plugging into the difference quotient over here and trying to find f of x plus h and then f of x and then subtract, I can just do the simplified difference quotient and I can plug my values straight into 2x plus h. Let's try it with the values we just did. Notice that this question has the same x values and the same h values that we did last time, except for now instead of plugging into the original difference quotient, we're going to be plugging it into 2x plus h. So I get 2 times 4 plus 3, which is 11. That's the answer we got before, but so much simpler. Again, we're going to get 2 times x plus h. Once again, we got the same answer as last time, but much faster. Let's see this one. 2 times x plus h. And once again, we got the same answer as last time, just a lot faster. So you can see that simplifying the difference quotient first, once, then we can plug in all of our values after we simplify the difference quotient. That's going to be much faster. Hopefully you've been convinced that simplifying the difference quotient for any function is the better route to go before we plug our values of h and x in. So for the next 2 examples, we're going to practice finding the difference quotient given a rational and given a radical. Let's start with a rational function. The first step is always finding what is f of x plus h. That is going to be 3 over x plus h. And now we're ready to plug that into our difference quotient. We're going to take our difference quotient and replace f of x plus h with 3 over x plus h. We're going to replace f of x with 3 over x, and then we're going to have this all over h. So to get rid of our fractions within fractions, we multiply by the LCD. And that'll cancel out these denominators. Let's just show our work. Once we multiply it out, then we can get rid of some of our fractions within fractions. This x plus h will cancel out. This x will cancel out. We'll be left with 3x minus 3 times x plus h over x plus h times x times h. Now take care, you can't just cross off the x plus h and x plus h because there's multiple terms up here. So we're going to have to distribute that minus 3, see what we get from there. So we get 3x minus 3h over x plus h times x times h. Now that numerator can simplify a little bit. You get 3x minus 3x. So we'll be left with negative 3h over x plus h times x times h. And so I see there's a factor of h in the numerator and a factor of h in the denominator. So I'm going to cancel that out. And I have negative 3 over x plus h times x. You can multiply that out if you want. You get x squared plus hx. Either one of these would be acceptable as a final answer. So I'll go ahead and let you decide whichever one you like best. But when you get new values of x and h, you can plug it into this simplified difference quotient. It'll save you a lot of time if you know how to find this difference quotient. That way when you plug in values of x and h, it's going to be much easier. Let's go ahead and do the last example. For this last example, the function that they gave us is the square root of x. And it's always helpful to identify what is f of x plus h. That would be the square root of x plus h. And now let's write our difference quotient. And then let's replace f of x plus h with the square root of x plus h. And then f of x with the square root of x. Now that might look like it's in simplified form, but there's a problem with this. We don't want to have an h in the denominator for reasons that will be described in future lessons. So how will we get rid of that h in that denominator? Well, we're going to rationalize the numerator. That is, I'm going to multiply this fraction by a fraction with the conjugate, meaning I'm going to put a plus sign here. And then I'm going to make the denominator exactly the same so that this fraction is equal to 1. That means I'm not changing the value of this difference quotient, I'm just rewriting the way it's written. And so when I multiply it out, I'm going to get the square root of x plus h squared minus the square root of x squared. That's because these are conjugates, so when I multiply them, I get the difference of squares. And then the denominator will be h times the square root of x plus h plus the square root of x. Can I simplify that numerator? I sure can. Square roots and squares cancel out, so I'm left with x plus h. And square roots and squares cancel out, so I'm left with x. And then I can simplify my numerator. So it's going to be x minus x. So I'm left with h over h times this whole denominator thing in the parentheses. So now my h's will cancel out, and I'm left with 1 over the square root of x plus h plus the square root of x. Now it might not look more simplified to you, but the reason we did this is because we don't want a factor of h in the denominator. So we always have to be mindful of that. Whenever you're finding the difference quotient, you have to remember that there's a minus here, and potentially that minus needs to be distributed to whatever the f of x term is. So if there's more than one term, you have to distribute that minus there. But if we do it correctly, that numerator will always have pieces that cancel out, and you'll always be left with something that's just a factor of h. And that factor of h will always be able to cancel out with that h in the denominator. And whenever we do that, we'll end up with some fraction that does not have a standalone factor of h in the denominator. So that's when you know you've done a good job. And that's the difference quotient here. And that's it for today. So go ahead and practice that. When we get to the next section, we'll see why finding the difference quotient is so important. Have a good day.